Trigonometric substitution. Not a lot of people really like this method because it's pretty challenging and very tricky. But through this video, I'm actually going to make it as simple as I can, and I'm going to do it step by step so that you understand how we go about doing trigonometric substitution. It's really not that bad. It's just that the questions that they ask is sometimes really, it's intense. It is pretty intense, but it's actually really not that bad if you see the patterns. So in this video, I'm actually going to be covering the ones where we have like two terms in the denominator, like this, so that we can this is the first part of the trig substitution, and then the second part of trig substitution is when we have trigonometric functions within the integral. But in this is part one of trigonometric trigonometric substitution with integration. So part two will be based on the other type of substitution when it comes to trigonometry. Okay, so this also, look at the timestamps. It's according to what we have, example 1, example 2, example 3. So whichever one you want to watch first, or whichever one you want to watch badly, then go for it. But I'm going to be covering all of them in this video. So let's just first get into the introduction of this type of trigonometric substitution that we are going to do in this video. So I'm not really going to show an example yet, but what I'm going to be doing is just a little introduction here. So what I want you to be aware about is the three types of things that we'll see in order to know that we are going to use trigonometric substitution. So I'm going to write them down quickly over here. One of them will be x squared plus a squared raised to the power of n. The other one will be x squared minus a squared to the power of n. And then the third one will be a squared minus x squared to the power of n. This is number 1, this is number 2, and this is number 3. Okay, so the first one, what are we looking for over here? So if we have some type of integral where we have the denominator consisting of two terms such as this with two perfect squares, either adding each other or subtracting each other, we are going to resort to this trigonometric substitution method. So for the first one, when we need to substitute for a trigonometric function, we're going to let x, in this case over here, because that's our only variable, where a is actually a constant. I should have said that in the first place. A is a constant and n is also a constant, but n is obviously an exponent and a is the base inside of the denominator. Okay. So we're going to let x equal to a multiplied by tan of theta. Okay, so that is the substitution we are going to be making. So we're going to replace our x value with a multiplied by tan theta. So that's just the first step that we're going to take. This is only the introduction here. And then when we get to the examples, I'm going to show you how we go further and progress with these steps. So the second one is x squared minus a squared. You can see it's a difference of two squares, but we're not going to separate them like we would normally do. Okay, so what we are going to do, whenever we see x appears first before the constant, when it's subtraction, we are going to let x be equal to a multiplied by secant theta. And then with the last one over here, when you have the constant before the x, the variable, then therefore you will let x be equal to a multiplied by sine of theta. So if you are returning and you have already learned trigonometric substitution and you're still a little lost, I'm pretty sure you'll catch on it immediately, right? But if you are completely new and this is your first time looking at this and your lecture hasn't gone over it yet, then I know you will get a little bit confused, and that's why I said we're going to go through some examples and then we're going to apply them and it'll be much easier to use them. Okay, so just keep this in mind. I do recommend writing all of this down. So just write all of this down on a piece of paper or whatever you have right next to you, and then I want you to, while I do the solution, just read the stuff out loud to yourself, and then if I say the correct one, you're like, oh yes, this is why we're using it. So that's a good use, and it's good to stay interactive and not just watch the video like it's some random YouTube video. Okay, we're learning here. So let's move on to the first example. So the first one is the integral of dx over x squared plus 25. Now, we're so used to this at this point that we know we just have to rewrite it as integral of 1 over x squared plus 25 with respect to x, because we want to take the dx outside of the fraction, so it's easier to read. Okay, so now what we see is the following. So if you can remember previously, what I told you, that we had something along the lines of x squared and a squared, right, in a bracket. So we had something like x squared and then a squared raised to the power of n, but depending on what sign we have, in this case it's addition, so we're going to add that there, right? We are going to follow a certain substitution where we're going to let x equal to something based on this. But first, let's just break this down, okay? So we're going to say equals, and we're going to actually do the following. It's going to be 1 divided by, and it's x squared plus, and when you see a squared, remember that I said a is a constant. And a squared just means that it is multiplied by itself in this case, right? But 25 is a perfect square. Therefore, it can also be written as 5 squared. Can you see the correlation? A is just replaced with 5 over here. Or 5 is just going to be replaced with a. So that means, because it's an addition and we have x squared plus a squared, therefore our x that what we are going to substitute into our x is going to be a multiplied by tan theta. So it is tan theta. There we go. But now, just remember what I said. The 5 is replaced with the a value. So therefore, this is our a value. It's 5. Okay, now you got to this point and you're thinking, what do we do next? Well, what have we been doing with polynomial substitution? What we have always been doing was we were always taking the first derivative. So in this case, we're going to take the derivative, we're going to do implicit differentiation, and we're going to have dx by d theta is equal to 5, and the derivative of 5 tan theta, remember this 5 is a constant, so we can keep it out of it. But what is the derivative of tan theta? The derivative of tan theta is just sec squared theta. Okay, and now we just need to take this d theta on the other side so that we can get it into some form of integral. So dx is equal to 5 secant squared theta with respect to theta. Okay, hey, look at what we're doing already. We already know what our dx is, so that's what we're going to replace. Okay, now what we're going to do is, okay, so this is as much as we can do by now, but what I want to stress quickly is the fact that we need to do one more thing. And what is that? We need to do one more thing, and it's an indefinite integral, so no, it is not, we have to find the value. But what we do need to do is we need to find theta. We need to make theta the subject of the formula. And the reason why I'm saying that, you'll see towards the end of this example why I'm making theta the subject of the formula. So let's just quickly do that. So over here, how do we do that? We're going to use that equation. X is equal to 5 tan theta. We're going to have 5 tan theta, I'm just going to swap them around, is equal to x. And then we're going to divide both sides by 5. Then we're going to have tan theta is equal to x over 5. And in order for us to get theta on its own, we're going to arc the tan on the other side. So it's going to be theta is equal to arc tan of x over 5. And there we go. Now we got our theta. So now that we've got all of that, the only three things that we mainly need with these trig substitutions, with this method, is our x, our dx, and our theta. Theta comes later. But right now we're more focusing on the x and the dx. We're replacing the x and the dx to make this integration easier. Okay. Now, we need to do the replacement. Also, I forgot to put in dx over here. Okay. So there we go. Now we need to replace dx. So let's do that. Dx is equal to 5 secant square of d multiplied by d theta, right? So that's going to be the integral of, and I'm just going to put the 5 secant theta, secant square theta at the top, and d theta would be outside the fraction like that. Okay, just to make it easier to read. And then what we have at the bottom is this. But note that we still have x over here. And what is x equal to? Remember that x is also equal to 5 tan theta. So we're going to replace 5 tan theta with x. Meaning that we're going to have 5 tan theta raised to the power of 2 plus 5 square. Okay, so now you can see that we don't have a single x. We only have theta. That is perfect. That is exactly what we want to do. And that is what this trig substitution is all about. And now what we need to do, we need to just keep simplifying. So we have the integral of 5 secant squared theta divided by, and then we're going to take the square into these two over here, the 5 and the tan theta, and you can write this as 5 square multiplied by tan square theta plus 5 square with respect to theta. And now what we can do over here is we can take out 5 square as a common factor. And that's exactly why we did this in the first place. So that we can take out common factors and make life so much easier for ourselves. So we're going to say that this is the integral of 5 secant square theta divided by, and then we have 5 square into tan, that is underneath. This is tan square theta plus 1. Okay, with respect to theta. Alright, now that we've made it this far, now we can actually do one more thing over here. Because now we have 2 terms in this bracket. But what does this look familiar to? This looks very familiar. Okay. This is a part of our identity that tells us that 1 plus tan square theta is equal to sec square theta. But obviously this is exactly the same as this because it's an addition and it's commutative, meaning the order does not matter. It doesn't matter where these 2 terms are, it will still be the same thing and it'll still equal to secant square theta. Therefore, this bracket will just be equal to secant square theta. So it'll be the integral of 5 secant square theta divided by, then we'll have 5 square multiplied by secant square theta with respect to theta. And now look at this. This is the best part. These can cancel out, and this will be 1 over 1, and this can cancel out, and this will give you 5 to the power of 1 in the denominator. Therefore, what we are left with is the integral of 1 over 5 with respect to d theta. It looks way better now. Now we can actually integrate with respect to theta. So what we are going to do is the following. We are going to remember the integral of let's say a constant with respect to, let's say, dx, for example, will be equal to the constant multiplied by x plus c. Okay, maybe I should have just said a instead. So let's say the constant is a actually. It will look like that. So therefore we're going to apply that exactly to what is going on here. It's going to be 1 over 5 multiplied by what they have respect to, which is theta plus c, because it's an indefinite integral. Okay, we're almost done, don't worry. Remember that this question is not asking for in terms of theta or with respect to theta. It's asking with respect to x. So therefore, what is theta equal to? And do you see why I had to determine what is theta equal to? Theta is equal to arctan of x over 5. That's exactly what I wanted to do. So I just need to replace theta. And you can see that arctan of x over 5 only has a variable x. So we're going to do that. So it's going to be equal to 1 over 5. And then we're replacing theta with arctan of x over 5. And then we have plus c. And that is the answer for number 1. And this was a little bit of an introduction to the first substitution method for trigonometry. Then the next 2 questions are we're gonna increase the difficulty a little bit. Okay. Here's our next one. But this time we're working with a definite integral. So it's a little bit more different. So what we're gonna do is the following. We're just gonna rewrite it again. This is 1 and 0 upper and lower limits respectively. 1 divided by, and then we're gonna have x squared plus 1 raised to the power of 2 with respect to x. Hey, now look at that. So now what we're going to be doing is the following. So let's look at the denominator again. We have the same thing basically. We have this in the form, it's the same as the last question, we have it in the form of x squared plus a squared raised to the power of n, right? And n value, we actually have one this time, which is 2. This is where it gets a little complicated now. Actually, no, it's just extra work, not really complicated, if I would say. So what's going to happen here is the following. So we are going to say that because we have this, it's basically the same as the last one. We have the addition with the a squared and x squared, but we're going to just quickly break it down like this. This can also be written as, this is 1 and 0 here, 1 divided by x squared plus 1 squared, because 1 is a perfect square of itself as well. So therefore we do have perfect squares, which means we can apply trigonometric substitution. Therefore, because we have the addition, we're going to let x equal to a multiplied by tangent theta. But we know that the a value is equal to 1. So we're going to replace a with 1, which we don't really need to write anything. So therefore x is just equal to tan theta. Therefore we just need to take the derivative dx by d theta, which is going to be equal to secant square theta. And then we just get dx on its own. D theta. Okay. Now that we've done that, we need to actually, I just remembered, we got x now, and we got dx, but now we need to define a new limit now, a new upper and lower limit, because remember, we are doing a new substitution. And then we need to define new limits because obviously we're changing up the integral or the integrand. So therefore, what we're going to do is the upper u limit, or not, it's not even u anymore. I think we're doing, upper theta, there we go. Because remember, we're assigning a new variable which is theta. So upper theta, and then we're going to have the lower theta. The lower limit theta and the upper limit theta. And what are we using reference to? We're using reference to x is equal to tan theta. Remember, that's the change we have. So therefore, we're going to have tan of 1, which is the upper one, and tan of 0, which is the lower one. So therefore, we're going to have tan of 1, which is the upper limit of theta, and then the lower limit, we have tan of 0 over here. And now there's an issue, right? Now, if you have already done the stuff before, I'm pretty sure you already see the issue. We're not supposed to do this direct substitution from our x. We're actually supposed to have it in terms of theta. Because if you remember from polynomial substitution, we had u as the subject of the formula. And then we could go on and do this method. So therefore, this will not work. So we need to first find out what theta is. So if you actually pick that up, then nice. So therefore, we actually have to solve for theta, meaning that we can actually just, theta is going to be equal to arctan of x. Okay, now that is where it catches people out. Some people actually just do it over here. And it's actually not like that. Because remember, I want you to write down like this. This is our x limit, and this is also our x limit. That is what we should know, and therefore we have to sub those into x and not theta. Okay, great. Now that we got theta, we can actually do this now. So we got theta. Now we can do this. We can say the theta upper limit now, and we can say the theta lower limit, which is equal to, and there we go. Now we're going to say arctan of 1, which is the upper limit, and arctan of 0. Okay. And then this over here will just be, so arctan of 1 is just equal to pi over 4. And then arctan of 0 is just equal to 0, according to our graph. Okay. So now that we have these two, we have our new upper and lower limits, meaning that we're going to write it like this. We're going to have pi over 4 as our new upper limit, and 0 as our new lower limit. Okay. Great. And now we can just do the substitutions. So I always recommend doing dx first, and we know dx is actually equal to secant square theta multiplied by d theta. So therefore, we're actually going to put the secant square theta in the numerator. So that's going to be secant square theta divided by. And then obviously d theta is right here. Okay. And now, what else are we going to replace? So in the denominator, the only thing we're replacing is x. And what is x equal to? X is equal to tan theta. So that's the only thing we're going to be replacing right now. Okay. So now, we're going to have bracket, and it's going to be tan, but it's tan square theta, because remember, it's x square. Therefore, if we're plugging in if we're plugging in tan theta into x square, we're actually going to get tan square theta plus 1 square. And then this over here is just going to be square. But what I want you to realize is, please don't write the square whenever you have a 1, because you can't take out 1 as a common factor. I mean, you can, but it's not going to change anything. So that's why whenever you have 1 square, I don't recommend writing the square afterwards, because you only use the square to actually determine this, to know what substitution you're going to be using. Okay. Now we need to know our identities once again. This trigonometric substitutions is, if you don't know your identities, you are actually screwed. Okay. So what is this identity? We can clearly see that is the secant square theta identity. Tan square theta plus 1 is equal to secant square theta. Therefore, we can write the integral like this. Pi over 4, then we have 0, and then we're going to have secant square theta divided by, then we're going to have secant square theta all squared with respect to theta. And now what we can see over here is that we can cancel this with this over here. And then therefore we'll get pi over 4 over here and 0 over here. Then we're going to get 1 divided by secant square theta with respect to theta. And then we can also write 1 over secant square theta as, so we're going to have upper and lower limits. I have to keep doing that. We can also write 1 over secant square theta as cosine square theta with respect to theta. Great. Now we need to, now that it goes even deeper. I know, that's crazy actually. There's even more. So what we have to do is the following. So with this, it has a square. And that actually makes it a lot more challenging than you think when it comes to integrating this whole thing. Right? Because we can't write this down as some identity. Like, I know you can write this as, I think it's 1 minus sine square theta. But once again, there's the square again. So we need to use an identity that basically gets rid of the square and makes it a little bit easier for us to deal with. So what is that going to be? Now, it's from your double angles, by the way. But I have a simplified one where I have cosine square theta as the subject of the formula. So it actually looks like this. So cosine square theta is equal to 1 plus cosine square theta. I mean, cosine, double angle cosine theta divided by 2. Now, if you only know this one, right, cosine 2 theta, if you don't have this as your identity that you're given in university or college, then I do recommend using your original cosine 2 theta, which is equal to, I believe it was 2 cosine square theta minus 1. I think it was that one. But I normally use this one. Okay. So I do recommend using this one just to make life easier for you. And you can see, we've eliminated the squares. There is no square. So we're just going to rewrite it exactly how I just did it right now. So it's the integral pi over 4 and 0 here. And then it's just going to be written as 1 plus cosine 2 theta divided by 2 with respect to theta. Okay, now that we've got that out of the way, what we have to do is we need to break up this fraction, because you can see we can do it. This is going to be the integral pi over 4, 0, and then we're going to have 1 over 2 plus cosine 2 theta divided by 2 with respect to theta. Okay. And then what we can do now is we can actually just break these up. Okay, and this is how we break them up. You should know how to like linearize these ones already. So we actually write it like this. It's going to be integral pi over 4 and 0 over here. But as you can see, this is just a constant. So we can just take that constant to the front over here. And then this will just be 1 d theta. Okay, because 1 is the only thing that's there. So yeah, this is plus. And then as you can see, this is just a half multiplied by cosine 2 theta. So we can actually just take the half out like this. Integral pi over 4, 0, and then we have cosine 2 theta. And this one is also with respect to d theta. Okay, so now that we have all of that, we can integrate. But before, we can only integrate this one actually. So we can integrate that one, but not this one yet. We have another complexity over here. I don't know how to say that word. So we have something a little complex over here, which is the 2 theta. So we're going to take a trip back to U substitution. Ooh. Because we're doing 2 substitutions now. That's crazy. But yes, we're using U substitution. So this is what I'm going to be doing now. Okay. So I'm going to let U be equal to 2 theta, right? So we can try and eliminate this little factor over here. So we can take the derivative on both sides. That's going to be du by d theta. And this is just going to be equal to 2, right? Derivative of 2 theta with respect to theta. And that's exactly what we have. Okay. Now, what we do is we have what du is, or that's not what we're trying to find. What we are trying to find is something to replace d theta, like this here. Okay. So in order for us to do that, we need to multiply both sides, divide both sides by a half. Divide both sides by 2, or you can multiply both sides by a half, and then you'll get d theta is equal to a half du. Hey, now we know what d theta is equal to, and we know what u is equal to. So which means we can just replace those things. We can replace the 2 theta over here with u, and we can replace the d theta here with a half du. Okay, so that's, now we're going to write it like this. And this one here, this first one here, we don't really have to do any substitution with that one, since it's pretty much straightforward to integrate that. I know if you want to, you can do the substitution, but what the heck. Okay, then this is just going to be equal to the integral. It's going to be pi over 4, 0, and then it's going to be 1 d theta. Now, and this is a half. And now there's just one little thing that we still have to do. Remember the upper limit and the lower limit, we still need to find the new ones. Because remember, we just did a new substitution method. So we need to find the new upper and lower limits. So I'm just going to write down over here that we need to find out the upper limit and the lower the upper u limit and the lower u limit. Okay. So then how we're going to do this is the following. We're just going to use this. We're going to substitute our old thetas. And what were our old thetas? Our old thetas were theta is equal to pi over 4 and theta was equal to 0. Okay. So then we're going to do the following. It's going to be 2 multiplied by pi over 4, which is just going to give us pi over 2. And then 2 multiplied by 0 is just equal to 0. Okay, so now we have our new upper and lower limits. So it's going to be pi over 2 and 0. You can see that whenever you make new substitution methods, you have to find new limits. Otherwise, it's going to be completely wrong. Okay, because you're finding a new way to go about integrating. Okay. Now we need to do our substitutions again. So we're substituting 2 theta with u, so it's cosine of u. So it's cosine of u. And remember, we have a half du, so that's going to be a half du. But what I want to do is I want to take this outside, because remember, you can do that, because it's being multiplied. So it's going to be half times a half, which is equal to a quarter. So this is with respect to u. Great, now we can integrate them perfectly. So, when we are going to integrate them, this is how it's going to go. Okay, so we're going to integrate this one first here. And this is going to be a half multiplied by And now remember, it's definite integrals, meaning that we're going to do the following. So obviously this is just going to be theta. The integral of 1 with respect to theta is just equal to theta. And then we have pi over 4 here. And then 0 over here. And this is plus a quarter. And then we're going to have the bracket over here, like this. And what is the integral of cosine of u? Integral of cosine of u is just going to be positive sine of u. Okay, and then we have pi over 2 here, and we have 0 over here. Now we just need to evaluate. Okay. Now, because there are definite integrals, we don't really need to worry about substituting back now. Okay. So we're just going to find, with respect to our new limits, we will immediately have the answer. Okay. So then this is just going to be equal to, I want to actually start with the left-hand side first and the right-hand side. So I'm going to do it in different colors. So this is the left-hand side, and then this blue over here is the right-hand side. So let's start with the red first. Okay. So the red will be equal to, we're going to have a half multiplied by theta, which is actually just going to be the upper limit first, so it's going to be that, minus a half multiplied by 0, which is just going to be equal to, and that's going to be pi over 8 minus 0. So that's going to give us an answer of 0 actually. So that's just pi over 8. Okay. And then over here, we're going to have the blue one. Okay. So the blue one is going to be a quarter multiplied by sine of u, which we're going to take the upper limit first. That's pi over 2. And then we're going to minus it by the one of the lower limit. I just took out a quarter as a common factor here. Sine of 0. And then we know sine of 0 is just equal to 0. So therefore a quarter multiplied by sine of a half, which is just going to be equal to a quarter. Okay. So it's just going to be a quarter. Because sine pi over 2 is just equal to 1. Now remember, we're adding them together. Okay. So now we're going to do the following. Now we can say that it's going to be, we're continuing again, pi over 8 plus a quarter. We're just going to write this together, pi over 8, and then you can write this also as 2 divided by 8, so that these denominators are the same, and then you can write it as pi plus 2 divided by 8, which is the final answer. There we go. It was a very long one, but this is a very good question to go over, especially if you are doing this. Like, I'm pretty sure this would be some type of tutorial test or examination question, potentially. Maybe the best examination question you can get, especially for finals, because this would be a nice one to get. There's worse ones, trust me. Let's move on to the final one, and then we can get it over and done with. Okay, this is the final question. But in this one, there's a twist. I'm going to go simplify as much as possible. And trust me, it's going to be so cool and satisfying when you actually understand how much I'm going to make this easy for you. This is a pretty intense question. And I know you can already see it because now, we have a fraction. Ay, that's nothing too different. It just means we're working with a square root. But now, this is where there's going to be a little bit of a trick. Okay? Let's just do the normal ones that we do, right? The normal procedure that we do. Let's inspect this denominator here. So we have some form like this, where we have a minus, so we have a negative, right? But the constant is before the x. So let's look at it like this. It looks like a square minus x square raised to the power of n. And n is just the rational exponent right there. Okay, great. Now, whenever we're working with, when we have a difference and the constant is first, we are going to substitute x with a multiplied by sine of theta. And what is our a value? Let's just determine our a value here. We're going to write down this integral again, but this time I'm going to skip the step over here. I know okay, it's an indefinite integral. I'm going to do this. It's going to be 1 divided by, and yeah, of course, we're taking our dx outside like that. And then I'm just going to break it down like this. It's going to be 3 square. 9 is also equal to 3 square because 9 is a perfect square. Minus x square, which is also a perfect square, raised to the power of 3 over 2. Okay, so therefore this indicates to us that our a value is 3. So we're going to substitute 3. Okay, So now that we have that, let's just find the first derivative. Implicit differentiation, we're going to say dx by d theta, and this is going to be equal to 3 multiplied by the derivative of sine theta is just equal to cosine of theta. Okay. Now, what we're going to do is we're going to get dx on its own, so it's going to be 3 multiplied by cosine of theta with respect to theta. Okay. And now what we see over here is we have something to replace dx with now. Okay, perfect stuff. So we can replace dx, we can replace x. Now we just need to be able to replace theta. Okay, so let's just see that right now. But later on, and I'm going to show you the twist that we are going to have to show you that you don't have to use the theta thing. Okay, but let's just do it anyway. So I'm just going to go fast over here, and this is going to be equal to arc sine of x divided by 3. So that's what theta is equal to. You can also do it by yourself if you want to. That's how it just makes theta the subject of the formula over here. Okay. So now that we have theta over here, and it's an indefinite, we can just start with the integral now. Okay. We can start substituting. So this is equal to the integral. That's a little bit of too big of an integral. There we go. This is going to be, we are replacing dx now. Dx is equal to 3 multiplied by cosine theta d theta. So we're going to put the 3 cosine theta on top. And then the bottom is just going to have the 3 square minus, and we're going to replace the x, by the way. X is equal to 3 sine theta, so we're going to do that. But because it's x square, we're just going to take the square in immediately. So 3 square is just going to be 3 square. No way. And then sine theta square is just equal to sine square theta. Okay, so I just did it immediately. And then dx. Write that a little bit to the side. There we go. Now we need to, it's pretty much obvious here what we have to do. We must take out 3 square as a common factor, and then we'll have 3 cosine of theta divided by, then we have this divided by, we're going to take this over here, 3 square into, I could write a square bracket instead, it's going to be 1 minus, that's sine square theta, like that. Okay, and then it's like this, 3 over 2. Alright, and now what we're going to do is the following. We can also do this. Now, let's look at this exponent outside. We can take this exponent into this, and we can also take it into that. But let's first take it into the one to the far left, which is this one right here. We can multiply them together, the exponents, due to exponent laws of multiplication. So this is the integral of 3 cosine theta divided by, and then we're going to have, let's just write it here. If we have 3 square, which can also be written as 3 to the power of 2 over 1, multiplied by, or like this, sorry, this is going to be that, to raise to the power of 3 over 2. We note that this is actually, this can also be equal to 3 to the power of 2 divided by 1 multiplied by 3 to the power of 2, where these will these will cancel, and this will be equal to 3 to the power of 3. Okay. So therefore we can actually just write this as 3 to the power of 3, which is outside of the bracket now because it's already been affected by this exponent. Alright, now we just need to do something else now. Okay, so what else are we going to do? Now, this 1 minus sine square theta can also be written as cosine square theta. According to our identities, sine square theta plus cosine square theta is equal to 1. And if we make cosine square theta the subject of the formula, or if we just take the 1 over and we take the cosine to the other, let's not do that one. We take the sine over to the other side, so that we get something like this. It's going to be cosine square theta is equal to 1 minus sine square theta. Okay. So then we have exactly the same thing over here and here, which is equal to cosine square theta. That's what we're going to be replacing it with. So this will be multiplied by cosine square theta raised to the power of 3 over 2. Okay. And now we just still need to manipulate. Also, I just realized I'm not writing my dx's over here. please don't forget to write your dx's because it's important with the integration. Otherwise, they'll not mark it off. Okay, notation is really important. Integral of 3 cosine theta divided by, and then we're going to have 3 cube over here. And we can also write this, by the way, this whole thing over here, including the exponent, as cosine theta raised to the power of 2, all raised to the power of 3 over 2, which then we can write this as cosine theta, where we have 2 divided by 1, which this is also 2 divided by 1, by the way, multiplied by 3 over 2, where these 2's will cancel, and then therefore we will have cosine theta raised to the power of 3, which we can also write as cosine cube theta. Okay, great. Now from that, we can write down cosine cube theta. Okay. Okay, now that we have done that, what we can do is the following. We can start cancelling with respect to x, by the way. Am I saying x? Wait a minute, hold on. Something's not right. Oh, there we go. That makes a lot of sense. It's theta, guys. Guys, if you are screaming at me behind that screen, or if you just left the video, I do apologize. Something was not right. I was just so focused on dx. I don't know why. But yes, we have d theta. So that was the huge mistake that I've made. So yeah, penalize me for that. So we can cancel these out. This will be 3 to the power of 2 in the denominator. We can also cancel these out. It will be cosine squared theta in the denominator. Therefore, we're just going to have 1 divided by 3 square multiplied by cosine squared theta with respect to theta. I'm just going to keep saying that from now on because I did mess up really badly here. Okay, and I do apologize. But yeah, let's just break this up over here. So what we can do over here is we can actually just take this out of the integral because this is 1 over 3 square, which we can actually take out as 1 over 9 because 3 square is 9. And then we can actually write it as 1 divided by cosine squared theta with respect to theta. And then we know that this is just going to be simplified as 1 over 9. And then we're going to have secant squared theta with respect to theta. Okay, lovely. Now we can actually integrate quickly. So, now we can actually integrate, right? Now the reason we can integrate and when we have this square over here is because this is actually an antiderivative of something specific. Well, what we know over here, what we remember about the derivative of tan of x is equal to secant square of x. And if you take the antiderivative of secant square x, that is just equal to tan of x, which is exactly what's going on here. So therefore, the antiderivative or the integral of secant square x is tan of x. Okay, I almost got lost on what I was doing. Like I said, we need to know a lot of laws over here, okay? Especially derivatives. If you don't know your derivatives, then it'll be a little bit more challenging to do antiderivatives. Okay. Cool. Now this will be, whoa, why is my derivative still there? This is supposed to be a bracket here. This will be tan theta, and then this is plus c, because we just integrated now. Okay. Okay, this is when remember when I said that I would simplify as much as possible. Okay, so tan theta, well, I mean, what you would have probably done was you would have done this. You would have plugged in arc sine of x over 3 into theta. I don't think anything is wrong about that. Okay, I don't know if you are allowed to do that, but what I want to do is I want to simplify as much as I can without the substitution. Okay, so what I'm going to do over here is the following. I'm going to break this tan theta up into sine theta over cosine theta. Okay, plus c. And this is multiplying, by the way. So therefore, what we have over here is it's going to be sine theta divided by 9 cosine theta plus c. Okay, we're getting somewhere. We're getting somewhere. Now watch this. we know that sine theta is actually just going to be equal to, where is it? Sine theta is actually just going to be equal to, okay, let me just write it here. Sorry, I skipped to this. That's why you don't have it. But sine theta, you can also write this, by the way, as sine theta is equal to x over 3, right? Because you're going to obviously divide both sides by 3 like this, and then you'll get x over 3, which is equal to sine theta. So sine theta we can replace with x over 3. Ooh, we took the cool way out here. We're taking the cool way out here. So this is going to be x divided by 3 all over, and then this we'll have plus c. But now this is the part where I feel like I needed to include this in the video so we can feel very confident in our mathematics. Now, let's look at this, right? Cosine of theta. What else can we write it as? Now, let's just refer this towards the sine square theta plus cosine square theta is equal to 1. And then what we are going to do is we're going to try and make cosine square theta the subject of the formula, so that we can have cosine square theta equal to 1 minus sine square theta. Right? And then what we're going to do is we're going to root both sides, like this, such that these will cancel out. And then therefore we have cosine of theta is equal to root of 1 minus sine square theta. Now this is amazing stuff. Because now look at this. We have sine theta now. So we can just plug it in like that. Okay, so therefore cosine theta is just equal to 1 minus sine square theta. Now this is what we're going to do. We still have the 9, so it's 9 multiplied by the square root of 1 minus sine square theta. Okay. I feel like there's something... Oh, no, there's nothing that I'm missing. Okay. So this is what we have so far. Plus c, obviously. So I'm going to write the plus c here. And then what we're going to do, we can actually, let me just quickly write this down over here. Remember that this is also divided by 1. So we're going to tip and times this one here in the denominator. Therefore, it's going to be x over 3 multiplied by 1 divided by 9 root 1 minus sine square theta. This is still plus c over here. And therefore, we can actually write this as a fraction where we have x in the numerator. And then in the denominator, we have 3 multiplied by 9. So what I'm going to do is I'm going to say 9 multiplied by 3 into the square root of 1 minus sine square theta. Okay, now that we've got that out of the way, we need to substitute sine theta. But how can we do that, right? We know that we can write sine square theta as sine theta all squared, like that. Okay, and then over here, because of that, we know what sine theta is. Sine theta is equal to x over 3, which was initially inputted there. So we have x divided by 9 multiplied by 3 into the square root of 1 minus, now x divided by 3 all squared is just going to give us an answer of x squared divided by 9. Okay, we have x squared divided by 9. And then this is going to be plus c. Okay. Okay. Now we have everything in terms of x. You can leave it here, but I told you, I'm gonna simplify it all the way. X is in the numerator. And now let's just take note of this over here. Whoa, no. You see, it's stopping me from winning. I want to win, man. So over here, what do we note? Now, we can actually take this in so that we can actually get rid of this fraction here, right? Now, we know that we can write we can write 3 as the square root of 9, right? Therefore, if we look at this entire thing over here, represented here, we can look at this as the square root of 9 multiplied by the square root of 1 minus x squared divided by 9. And you can also write this entire square root as 1. So it'll be 9 multiplied by 1 minus x squared over 9, like that. And what you can see, we can multiply the 9 in, where this 9 will be multiplied by 1, so this is what it's going to look like. So it's going to be 9 multiplied by the square root, so inside of the square root over here, 9 times 1 is just 9, minus 9 multiplied by, so 9 over 1 multiplied by x squared over 9, these cancel. And therefore, we're just left with x squared. This is just equal to x squared. Over here, plus c. And that is our final answer. Now that is the first part of the trigonometric substitution. I just thought it would be cool to do this part of the question. Just do it this way. I think it's a cooler way. And if you can even do this yourself, consider yourself a master in mathematics. Absolutely amazing.